So now you see two problems. The first problem, you're given an nth order differential equation, right? This is an nth order that n can be 3, can be 5, for example. So it's for this higher order differential equation, just one single equation, can you reduce it to the first order system? Yeah, you know this technique, but now apply it. Apply it. That means you will have more equations, but the order of each equation will be only first order, right? So you have a system of first order. So this given equation is nth order and non-homogeneous linear equation. Afterwards, you will get first order system, also non-homogeneous, also linear. Yeah, so you see from linear higher order equation to a linear first order system of equations. Now let's think about it. So to give you a hint to this problem, I will consider a third order equation. Let's think about the third order. How do we reduce it to third order? So let's say I have a x right here, third order, plus some coefficient times, okay, x the second order. You see this coefficient will be the coefficient of second order derivative. Let's use a2. It might depend on t. And then here, x first derivative. So let's call it a1, some coefficient given. It can also depend on t. And the function x, the coefficient of x is denoted by a naught. And the right-hand side is some function of t. So I will use a very specific case. This one, see, corresponding to the general case, I gave a specific case to give you a hint on how to reduce the equation of third order to first order system. Recall that we actually do a change of variable, right? So suppose we rename it. So if your x, we call it z1, this is z2, this is z3. So I just rename these derivatives. And this x, you do not have to rename it. That's unknown. But for the consistency, so we also consider x as one unknown, we can call it z1. So we can see that z1, z2, z3, they are related because z1 derivative is z2, right? z2 derivative is z3. And what is z3 derivative? Z3 derivative will be this term, right? X third order derivative. So we can think about that. What is Z3 derivative? So let's give that equation just a little more room. So Z3 derivative will be that one, which is negative a2 times Z3 minus A1 times Z2 minus A0 times Z1 and plus R of t. So now you'll see three equations. So first equation, second equation, the third equation. So yeah, third order equation, the originally given third order equation is now reduced to a system of first order equations. So we see the system. But now if you want, you can write the system into a matrix form. So let's put the three equations into a system. So certainly you can put a Z1, Z2, Z3, right? These are functions of t, and derivative of this vector is equal to the first one, this vector field, which is Z2, Z3, and the long one will be minus A2, Z3 minus A1, Z2 minus, yeah, so you see I'm trying to copy this portion, right? So, but of course, this vector field can be written as a matrix times a vector, that form. So we can just simply write this into a matrix, which is a matrix times the vector Z1, Z2, Z3. So think the first row will be 0, 1, 0. The second row of the matrix will be 0, 0, 1. The third row of the matrix is, see, we can look at the coefficients, right? Coefficient of Z1 is negative A0. So you put a negative A0, and here Z2 will have a coefficient negative A1. And then Z3 has a coefficient negative A2, negative A2. But still we have this R. So we need to, in addition to have this, we still have R. So that means we need to add a vector, which is, so let's write, to include a vector. So this is our system under consideration. So in addition to this name, I didn't use the Y. Instead of Y, we are using X, right? So let's do a quick change to see our, right? It doesn't matter, it's the same problem, except a different name. So we're solving a third order equation for X. So this system can be written as a first order after we do a change of variable. You see this Z1 is same as X, right? So that's our X. That's the unknown function in the original system. But Z2 is actually X derivative. Z3 is X second order derivative. So that's a change of variable. So in our new system, we have three unknowns. That means not only X is to be solved, unknown component, right? Which is Z1 now. Also those Z2, Z3 are unknown components. So now we have this Z vector. We call it z vector, and we can write as, this is our z vector whose derivative is equal to a certain matrix, which is possibly depending on t, because depending on the coefficients. You see, if those coefficients are given as functions of t, so this A matrix can be depending on t. And then times the z vector plus the right-hand side. This is another vector, which is denoted by b, that can also depend on t, because this r can be depend on t. So you see now we have a first order system, right? This is a system. Is first order, a system of three equations. It's a linear system and non-homogeneous if the original given equation is non-homogeneous. Yeah, so that's the hint. So if you can do this particular problem for third order, I'm sure you can extend this technique to represent this nth order equation, right? How do you represent in a system of first order? Okay, so you just need to determine the matrix A. Also determine the vector B. So you see the vector B will be related to this R, so it can be represented, right? So think of that, the special case, and that technique and idea can be generalized to this case. As a practice, you can work on the number two. Number two, see, this is a second order, right? The coefficients are not depending on t. That means we have constant coefficients for this second order equation. And it's homogeneous because the right-hand side is 0. So can you reduce it to a linear system of two equations? Yeah, so reduce it to first order. So now that means you try to decide A. Yeah, so here you try to decide A, which is a 2x2 matrix. So just try to think of the technique of problem 1. And this is a very special case. Instead of nth order, you just have a second order, right? So you will get two equations of first order. So that is a system of two equations. So this is just the application of the technique we just discussed. So after you get the first order, then we have recently talked about the solutions or general solution for the linear system of first order. So now, can you find the fundamental matrix of this system? Yeah, fundamental matrix. Remember, we denote it by G. G, that fundamental matrix. So for this case, you will discover that your A is constant, right? Because we have constant coefficients. So after you reduce to the first order system, and A is also a constant, you will discover this case. A does not depend on T, which can simplify the matter. That means when you find the fundamental matrix, yes, you can, for example, try to use the A to a certain power if you can discover a pattern for this A to the certain power. If you know A, right, once you rewrite this problem into this form, you know A. So A to the certain power, you can possibly find a pattern for this power of A. Then this is the power series expansion for the fundamental matrix. So you can use that technique K from 0 to infinity to discover the fundamental matrix. Yeah, so the important thing is that you want to decide a pattern, right? So then once you find that, then you can possibly find the fundamental matrix. So if you discover this after you get this summed up, and then if you find finally the fundamental matrix, then can you verify for this particular problem, can you verify that Liouville's formula is true for this fundamental matrix? Yeah, what is Liouville's formula? So Liouville's formula says that if you have G, the fundamental matrix for A, then determinant of the fundamental matrix can be written in this form. That is e to the integral. You see this part, that is a function of t, right? E to a certain t, a function of t, is definitely non-zero. So this, to show that this is a non-zero quantity, also shows that if a determinant of a matrix is non-zero for n and t of certain interval I, then this fundamental matrix has an inverse, because we know determinant is non-zero, implying that the fundamental matrix is invertible. So it has an inverse always. Yeah, guaranteed that G inverse exists. So as long as you find the fundamental matrix for the system and the fundamental matrix is invertible. And we remember that we use the G inverse to represent the general solution for linear system of this kind, right? Even, yeah, so if you know, no matter it's time dependent or not for the matrix A, if you have even a non-homogeneous, then you can represent the general solution using fundamental matrix for a linear system. So the inverse is used. Inverse of the fundamental matrix is used in that representation for the solution formula of a linear system. Okay, so that's the remark for these two problems. So I hope you continue to work on this problem. If you have any questions, please ask me.